So the title that I gave was Novel Probes of the Primordial Liquid, and we'll get to the novel probes in the second half. I'm going to introduce what I mean by primordial liquid via an extended introduction aimed at the students in the audience. And this primordial liquid can be seen as a part of the answer to two questions that many of us have asked since we were little children. So one of those questions which little kids ask is, well, what's this made of? And you tell them, and then you say, well, what's that made of? And then you tell them, and they say, what's that made of? And then what's that made of? And what's that made of? So, and how do these possibly elementary elements of matter fit together to make the larger thing that we started with? So at the cartoon level, you have a chunk of matter. What's it made of? Atoms. Well, what are they made of? Nuclei and electrons. What are they made of? Protons and neutrons. What are they made of? Quarks. So this is one of the stories that we will be following in this extended introduction. And then the other one, also a question that children ask, well, where did that come from? And you tell them, and then where did that come from? Where did that come from? So where did stars come from? Where did atoms come from? Where did protons come from? And this is a question that we'll come to in a few minutes. Here in cartoon form, this is the universe today. This is when galaxies formed. This is when atoms formed. This is when nuclei formed. This is when protons and neutrons formed. And we're going to be going back to here in a little while. But let's start with this story. And I'll start with this story going back to around 1905. And by that time, it was known that atoms had electrons in them. The electrons were negative. And they were neutral, so there had to be positive charge somewhere. And the positive charge was thought to be filling the atom in some sort of a pudding. That was J.J. Thomson's word. That idea was wrong. It was discovered based on Geiger and Marsden's experiments. It was discovered by Rutherford that no, the positive charge is all at the center of the atom in this hard point-like thing. Turned out to be not zero size, not a perfect point, but it was 100,000 times smaller than the atom itself. Now, how did Geiger and Marsden and Rutherford discover nuclei? What was the microscope they used to see inside the atom? They did a scattering experiment. And in many ways, actually, the most important thing that Rutherford and Geiger and Marsden did, I think even more important than discovering the nucleus, was to introduce a method for studying the structure of matter that has been used ever since, which is to, well, if you want to study the structure of the atom, scatter something off of the atom and look and see how it bounces. And by looking and seeing how your scattered particles bounce, you learn something. Because what was expected by Rutherford based on the pudding model was that these alpha particles that he was using to scatter off the atom would just go through. So the expectation was he had a source of alpha particles, and they would go through this gold foil with some very, very, very slight deflections that he was planning to measure. And instead, he saw these large angle scatterings, and that's how he discovered nuclei. The size of this experimental apparatus was about this big, I'll say. So skipping ahead, by the time we get to the 1930s, it was known that atoms, well, they have a cloud of electrons, positive there's nucleus, I already said that. And the nuclei, I won't belabor this point, but by the 30s it was known that those nuclei themselves were made of protons and neutrons. The protons had charge +1, the neutrons had charge 0, and it was also known that protons and neutrons had a size that is around 10 to the minus 15 meters. Size that we're going to come back to many times. So by the 1930s, in this what's matter made of atoms, what are atoms made of, nuclei and electrons, what are they made of, protons and neutrons, we were here by the 1930s. Well, what are protons made of? By the 1960s, this was the question. It was not resolved 30 years after it was first posed. And in fact, not only was it not resolved, it was very confusing. What had happened between the 30s and the 60s was that dozens of short-lived cousins of the proton had been found. They all sort of looked kind of like the proton. Their charges, they weren't all +1. They could be +2, +1, 0, -1, or -2. They had a whole range of masses, but they all seem to have the same size. They're all about 10⁻15 meters in size. Much as Mendeleev figured out patterns of atoms, physicists, Gell-Mann and Zweig in particular, had figured out that the patterns of the masses and charges suggested that these protons and their cousins were all made of smaller things that they named quarks. The patterns were such that it was as if they were made of up quarks with charge +2/3, down quarks with charge -1/3, and heavier strange quarks. Also antiquarks with the same mass and opposite charge. And it was as if protons were made of a U, and a D, and you can check that adds up to +1, and neutrons were a U, a D, and a D, and you can check that adds up to 0. And some of the protons' cousins were as if they were made of 3 antiquarks, or maybe a quark and antiquark. All of this was as if. Why do I keep emphasizing as if? Because nobody had ever succeeded in kicking a quark out of a proton or finding an isolated quark. And in fact, to this day, nobody has done those things. So clarity started to emerge at the very end of the 60s when Friedman, Kendall, and Taylor tried to answer this question Rutherford style. They aimed the new 3-kilometer long, so remember the apparatus before was this size. Now we have a 3-kilometer long accelerator at Stanford accelerating a beam of electrons, and they shot this beam of electrons at protons, and they looked for large angle scattering. Now I've set you up to think that was an obvious thing to do, because I've skipped from Rutherford to 1968. Actually, this was not what most people were thinking about at all in 1968. The reason this is not what people were thinking about at all is people said, well, this is not going to teach you much, because if you shoot an electron beam at a proton and it scatters at a large angle, it's going to blow the proton into smithereens. How can you possibly learn about the proton by blowing it into smithereens? A smithereens being a jet of many, many, many integer charged proton cousins. We're going to speak about these jets a lot as we go forward. And indeed, no quarks were ever seen coming out of these collisions. But Friedman, Kendall, and Taylor looked for large angle scattering anyway. And they focused on the scattered electron, just as Rutherford had focused not on what happened to the atom, but at what happened to the thing that bounced off. So they followed Rutherford's logic, the same logic that Rutherford introduced 60 years earlier. This is their apparatus. Kind of looks like the Rutherford story. You can tell there's a beam coming in from the left, and there's ways of looking at the scattered particles. But this is the size of it. This is an actual photograph of the apparatus in 1968. That's a person there. And this is what they were doing at the cartoon level. You shoot an electron in. It hits, let's say it hits this up quark. The electrons get scattered off at large angle, and that's what they measured. But you've blasted this up quark, but what comes flying out of here is not an up quark. It's a spray. It's a jet of many particles, most of which have a quark and an antiquark inside of them. So how did that help? In a sense, well, first of all, what did they find? They won the Nobel Prize for doing this experiment. What they found was quarks. They found that the way the electrons scattered off was exactly what you should expect if, just as Rutherford found nuclei, there were quarks in, Rutherford found nuclei in atoms, they found quarks inside protons in exactly the same way. They found that the scattering is quantitatively just as it would be if there were quarks in there. But in a sense, this just added to the confusion. It won them a Nobel Prize, but in a sense, it just added to the confusion. Because it shows quarks are just as real as nuclei. You can see them in there. They're not as-ifs. They're not bookkeeping. They're real. But why can't anybody kick a quark out of the proton and study it in isolation? So in a sense, it added to the confusion, although this was the key discovery that led to clarity. Clarity came in 1973. Gross-Wilczek and Politzer in 1973 discovered the laws of nature that govern what's now called QCD, which is the theory of how quarks behave. So what they did was the analog of what Galileo, Newton, and Einstein did for gravity, and what Coulomb, Ampere, Faraday, Maxwell, Feynman, Schwinger, and Tominaga did for the theory of electricity and magnetism and light. Gross-Wilczek and Paltzer discovered the fundamental laws of nature that govern quarks, and that had better explain everything I've said so far. As I will explain briefly, this resolved all the prior confusion that I've described. It provides a quantitative description of all known phenomena involving quarks, and it's a core part of what is now called the Standard Model, which is a terrible name, by the way. It should really be called the theory of matter. The theory of matter includes the theory of electricity and magnetism and light, and also quarks. And the point of the colloquium is that this discovery, which explained all the confusion from before, opens new vistas for scientific investigation, and that's what we'll get to momentarily. But let me first, in a brief way, explain how the confusions were resolved. So quarks and gluons make up protons, and they are not so different than electrons and photons. Electrons have charge, you know that, and charged particles interact with each other by exchanging photons. Light is made of photons. It's governed by Maxwell's equations. This, in 3 lines, is Coulomb, Ampere, Maxwell, Faraday, Feynman, Schwinger, Tominaga. So by analogy, things seem pretty similar. Quarks have a new kind of charge. It's not electric charge. It's got to have a name. It was called color. Electrons are charged. Quarks are colored. So quarks carry color charge. And colored particles interact with each other by exchanging gluons. Sounds very similar. Gluons by themselves are governed by equations that look a lot like Maxwell's equations. Sounds pretty similar. There's one little difference. The little difference is that the gluons themselves are colored, whereas photons are neutral. That means gluons can exchange gluons. So I've made this slide sound technical on purpose. This difference sounds like a technicality, but Gross-Wilczek and Paltzer showed that this seemingly technical difference has profound consequences. They showed that because of that technicality, the force between electrons, whereas the force between electrons is 1 over r squared, the force between quarks, as you make them closer and closer together, it grows more slowly than 1 over r squared. And this is, loosely speaking, we say that quarks interact weakly when they're close to each other. Furthermore, their equations show that if you pull quarks apart, the force between them gets stronger and stronger. The force, in particular, sorry, I said that wrong. The force stops decreasing when they are more than a distance r apart from each other. And what is this capital R? Well, this capital R turns out to be 10 to the minus 15 meters. So this 10 to the minus 15 meters scale, which is the size of a proton, is encoded in the laws of nature that Gross-Wilczek and Paltzer described. The forces weaken when the quarks are much closer together than r, so much closer than 10 to the minus 15 meters. But if you kick a quark really hard, as in this cartoon, I kick this quark really hard, it's going to come flying out, and it's going to get farther away than the size of this orange circle, which is 10 to the minus 15 meters. And as this quark gets farther away than 10 to the minus 15 meters, the force between it and its friends gets enormous and stops decreasing. And it takes so much energy for this quark to pull against this force that energy turns into new matter, and you get this spray of particles. So I've described this rather pictorially, but all of this is in the equations that Gross-Wilczek and Paltzer discovered in 1973, although it took a long time to fully understand those equations. So the laws of QCD are precise and predictive. And one of the things that's most easy to understand immediately is why all the cousins of the proton have the same size. All the cousins of the proton are the size of this orange sphere here, because this orange sphere is 10 to the minus 15 meters in size. This is the length scale beyond which the force between quarks stops falling off, and you get the phenomenon that I described pictorially a second ago. So it was also immediately understood why Friedman, Kendall, and Taylor were able to see quarks, because when you kick them hard, you resolve them deep inside a proton where they are weakly interacting. So what Friedman, Kendall, and Taylor did was they had a camera. It was 3 kilometers long. They had a camera that allowed them to take a high-resolution photograph of where is one quark at one moment. When they looked at the scattered electron, that was the question they were answering. Where is one quark at one moment? And the equations that we use to describe these laws, in particular, if you look with slower shutter speed, turn out to be very difficult to solve in full. So they're very good at describing the answer to this question. But if you ask, well, maybe they can you please calculate the mass of the proton? Very natural question. It took 35 years to do that. But it's been done. This is examples from 2008 of first principles calculations from the laws of nature governing quarks and gluons of the masses of protons and neutrons and all these other cousin particles. The theory calculations as of 2008 are shown in red. The experimental measured values are in black, and they all agree. And there were even some predictions that were subsequently confirmed by experiment. So by this time of sort of the 20 years starting in 1973, it was understood that all of that past confusion was resolved. But already beginning in 1973, these new laws of nature opened new questions. And this always happens. Anytime a new fundamental fact about nature is discovered, it's always the case that if you learn something new and fundamental, it opens new questions. It opens new vistas for exploration. Already in 1974, Collins and Perry realized that if you could take a star's worth of atoms and smush them together by a factor of 10 to the 5, you would crush the protons and neutrons on top of each other and make quark soup. To all the experts in the room, I'm speaking to the students, not the experts, but the experts in the room, go back and read Collins' 1974 paper. It's really fun. And they didn't call it quark-gluon plasma. They called it quark soup. By the way, nature does know how to smush a star by a factor of 100,000. The sun has a radius of 7 times 10 to the 8 meters. Neutron stars are around 10 to the 4 meters in radius. So neutron stars are where nature makes quark soup. This is a very exciting area of scientific exploration today. There's increasing evidence that neutron stars that are twice as heavy as the sun have quark soup cores. Growing evidence, but I'm not sure whether I would describe this as 100% established. This is the topic for a different colloquium. The colloquium that I'm going to give, though, also starts in the 70s. By the 70s, via the work of many, it was realized that at high enough temperatures, you also cannot have protons and neutrons. If you can get to high enough temperatures, you will have, it was thought, a gas of quarks and gluons. This was named quark-gluon plasma, an unfortunate name, we'll see. It was expected that at high enough temperatures, we should have a gas of quarks and gluons. The temperature had to be above 2 trillion degrees. Why did you need to have these temperatures? Because at these temperatures, the quarks and gluons would be interacting, getting close enough to each other that the forces between them would weaken. That was the idea. And the only place in time where temperatures of 2 trillion degrees ever arose was the Big Bang. So what was realized in the mid-70s was that for the first 10 microseconds after its birth, the universe was filled with quark soup, we're going to see is a better name for it, but what was at that time thought to be a gas of quarks and gluons. So all of a sudden, from asking what matter is made of, we had a chance to ask where did things come from. There's this epoch back here. Let me make sure I'm holding the right one. Yes. About 10 microseconds after the Big Bang, when quarks and gluons combined to form protons and neutrons. And if you ask when did stars form, it was here. When did atoms form, it was here. When did nuclei form, it was here. When did protons form, it was here. So all of a sudden, we have laws of nature that are allowing us to talk about the matter that filled the 10 microsecond-old universe. And, well, I said that those laws are predictive and can be used to do calculations. For example, by 2010, these are calculations from 2010. There were results like this with smaller error bars already in the late 90s. We knew from the laws that were discovered in 1973 that at a temperature which corresponds to 2 to 3 trillion degrees in other units called MeV, it's around here, the energy density and entropy density and pressure of the matter that filled the early universe, so this is going back in time, hotter and hotter, closer to the Big Bang, there's this clear dramatic change in properties. And you can ask, what does 0.8 mean here and here? Well, 0.8 is relative to, for those of you who are undergraduates who've taken an introductory statistical physics course and you've learned how to calculate the pressure of black body radiation. 1 here is the pressure of black body radiation made of gluons and quarks. It's non-interacting gluons and quarks, and look at that. This is within 0.8 of it. So calculations like this in the late 90s seduced us into thinking that what we were expecting was a gas. It turned out that understanding what this hot quark matter actually is, how it behaves, what's it like, if you had a drop of it, what would it be like? We got that wrong until the experiments were done. So really answering this question had to wait until scientists reproduced droplets of the Big Bang by accelerating and colliding heavy nuclei. Way back in 1983, Veit Busha and Fred Goldhaber calculated that collisions with energies bigger than around 100 GeV, this is a unit that I won't explain, were needed to reach this new regime. In 1983, this was almost a factor of 100 times the energy that any accelerator could produce. So it took 20 years to do this, but since 2000, at the relativistic heavy ion collider at RHIC, collisions at 200 in these units have been done, and since 2010, at the large LHC, the Large Hadron Collider at CERN, collisions at 2,700 and now 5,000 in these units have been done, so much higher than the energy that's needed. So these collisions are recreating little bangs. You are colliding nuclei at high enough energy that you make a little droplet of the early universe, which then expands, explodes, cools, and forms ordinary protons and its cousins within about 10 to the minus 22 seconds. And that's a picture of one of the first little bangs ever produced in the laboratory. This is an early collision at RHIC. 2 nuclei collided there, and this is the debris of the explosion from a little droplet of the Big Bang that was formed there that lived 10 to the minus 22 seconds. Here is today's highest energy accelerator, the LHC, outside Geneva. Remember, we started off with apparatus this size. Now we have apparatus this size in comparison to the Geneva Airport runway, which is here. There's another picture of the tunnel. Here's an actual photograph of the inside of the tunnel with the accelerator that accelerates these nuclei to these incredible energies. And then you need cameras to take pictures of the explosions. There are 4 such cameras. Here's CMS. There's CMS for real. There's a cartoon of Atlas. Notice the person right there. So this is vast compared to the apparatus of 1968. There's Atlas for real. Here's LHCb. Here's Elise. And these are the kind of pictures you get when you collide 2 lead nuclei at these energies. So this was a little bang right here, droplet of the Big Bang produced in a collision in Geneva. This droplet of incredibly hot matter lived for 10 to the minus 22 seconds, exploded, and we get to study the debris. Just to emphasize, this is not just Elise. Here's such pictures from CMS and Atlas also. So what have we learned? As I said, understanding what hot quark matter is actually like had to wait till it was reproduced in the laboratory. These collisions really are making droplets of Big Bang. What we see is the debris. What can we learn? Well, the big surprise was that this is not a gas. This hot stuff that filled the 10 microsecond-old universe is not a gas, it's a liquid. By 2005, this was clear. And I'm gonna give you a sense of how we learned that this was a liquid. But by 2005, it was clear that the hot Big Bang matter produced in these collisions is a liquid, not a gas. This is ironic. Rutherford looked for pudding and unexpectedly found nuclei, which were points at the time. Freeman, Kendall, and Taylor were studying protons. They had no expectation of finding hard point-like things, but that's what they found. They were looking, and this surprise has the opposite character. Everyone was expecting a gas of points, and instead we found soup. Hot quark soup turns out to be very liquid-like. There's less internal dissipation as it flows, so this is a dimensionless measure of its viscosity, which happens to be called 8/s. this is a way of characterizing the viscosity, the dissipation as a liquid flows, and the dissipation in dimensionless units of this Big Bang liquid turns out to be less than that of all other known liquids except one. So the discovery that this is a strongly coupled liquid is what's made this subject interesting, really, since 2005. A gas would have been boring in comparison. So we got lucky. How was this discovery made? You might think it was Rutherford again. Actually, no. So I'm going to spend a minute explaining to you how we learned this was a liquid, and it's a completely different set of logic than Rutherford. And I'm going to teach you this logic by looking not at heavy ion collisions. I'm going to train your eyes by looking first at the one terrestrial fluid with an 8 over S that is almost as small as that of the quark-gluon plasma. It's it's a fluid of fermionic atoms at 10 to the minus 9 kelvins instead of 10 to the 12 kelvins. It's 21 orders of magnitude colder. And what you do is you trap a cloud of fermionic atoms in this cigar-shaped trap in the top picture here. Then you turn off the trap and you let it explode. You let the cloud explode. And this is a movie. You can actually take photographs as the cloud explodes. This process doesn't happen in 10 to the minus 22 seconds. It happens in seconds. So you can take pictures. And you see this thing exploding. And what you notice is that it's exploding in the equatorial direction, but it's not exploding vertically in the polar direction. This is a cigar-shaped cloud. It's not exploding in its long direction. If this were made of gas and you turn off the trap, in a gas, all particles are moving at random in all directions. If you have a trapped gas, you turn off the trap, the gas atoms will fly in all directions. This will explode just as much up and down as left to right. The fact that it explodes left to right but not up to down is because this is not a gas, it's a liquid. And in a liquid, you say, well, the pressure gradients are much greater across it than up to down. The pressure gradients are much less up to down. Pressure gradients drive the explosion. This is the logic of how liquids behave. And so you can just see by looking at this that it's a liquid. You can do this quantitatively, extract values of this dimensionless measure of the viscosity. It comes in at around 0.4. We'll come back to that. So now I'm going to show you data from the LHC on Big Bang explosions. These are collisions of nuclei. And if what you had was a hot gas, if the little bangs, these droplets of Big Bang matter, were made of a gas, all the explosions should be circularly symmetric, like this one. But you can see with your eyes that this is not circularly symmetric. You can see with your eyes that this is not circularly symmetric. This is not circularly symmetric. This one exploded with more force this way, less force this way. So what that means is that here I had a collision of two nuclei. The collision was off center. It made a blob of Big Bang matter that was not circular. It was shaped a little bit like that, perhaps, if it was very off center. And when it exploded this way and not that way. So when you look at the momentum flow in the detector, it's exploded this way, but not that way, or less this way. So this can be done quantitatively, which I will not walk you through. But analyzing those data in a quantitative way, which I will not do, taught us that the 8 over S of this fluid is between 0.1 and 0.2. This should be compared to what you get for, say, water, which is around between 1 and 10. Liquid nitrogen between 1 and 10. Soup in your kitchen, it's an even bigger number. For gases, you get numbers in the hundreds or thousands. So hot quark soup turns out to be more hydrodynamic than water, because water has a larger value of this dissipation parameter than hot quark soup does. So what have we learned? What we've learned is that quarks and gluons in hot quark soup diffuse. They don't fly freely. It is not a gas. They're always bumping into each other. But they're not confined into protons. There are no protons at these temperatures. So the physicists of the 70s, 80s, and 90s were half right. They were right that there were no protons and neutrons. They were wrong that what you would get was a gas. Hot quark soup turns out to flow like a liquid, but the quarks and gluons are always bumping into each other. It's very much not a gas. The mean free paths are so short as to be hard to define. So a way of saying this in one line is that quarks and gluons are not confined into protons, but they're also not free. They're in a soup. This aside is to say that string theorists, for their own reasons, have discovered other similar theories to QCD in which everything I've just said happens also. And this is a very interesting aside, which Guy mentioned once already. I don't have time to do it justice, although it will come up one more time. So I'm almost finished with the introduction. There's a beautiful analogy between the actual Big Bang and these little bangs. When we study the actual Big Bang, we look at it, the photons coming from the microwave background radiation from the hot Big Bang with which the universe began. These photons come from the universe when it was 100,000 years old. We study these fluctuations, analyze them quantitatively, and there's a theory that gives you this red curve, and getting that theory right involves knowing about the materials properties of the 100,000-year-old universe and knowing about the initial conditions for the Big Bang. Here we have little bangs in heavy ion collisions. They explode. We get data shown in the black points. There's a theory that gives the curves that go through them. Getting the theory to go through the data points involves learning something about the material that is flowing and the initial conditions of the explosion. So there's a beautiful analogy here that I don't have time to do justice to. I thought I would end this introduction with a reflection on what Vicky Weisskopf, a predecessor at MIT, wrote in 1977. So Vicky Weisskopf was the Director General of CERN in the early 60s. He was a professor at MIT for several decades. When I arrived at MIT in 1997, I met him very late in his life. In 1977, he was giving a talk about liquids. And it was in a celebration of Edward Purcell, who had done a lot of work on liquids. And Vicky wanted to talk about how impressive it was that Edward Purcell had managed to study liquids. And here's what he wrote. Assume that a group of intelligent theoretical physicists had lived in closed buildings from birth such that they never had occasion to see any natural structures. Okay, let's forget that it may be impossible to prevent them to see their own bodies, their inputs, their outputs. We'll forget that. What would a group of intelligent theoretical physicists be able to predict from fundamental knowledge of quantum mechanics? The way we would say this, from the laws of nature, we'll take a group of theoretical physicists, give them the laws of nature, and ask, what do these things describe? Vicky said in 1977, they probably would predict the existence of atoms, of molecules, of solid crystals, of metals, of insulators, of gases, but most likely not the existence of liquids. So what's amazing about this quote is that it was in 1977. In 1973, all the theoretical physicists on the planet Earth had been given the laws of nature that govern quarks. They had 37 years to see what those equations predicted. Those theorists for 37 years had fundamental knowledge of the laws of governing quarks and gluons, but they did not predict that a hot quark soup was a liquid until it took the experiments beginning at RIC, now at the LHC, to teach us this fact. So Vicky Weisskopf was correct. So where are we in heavy ion collision physics? By recreating droplets of the matter that filled the microseconds-old universe, we've discovered the first liquid that ever existed, the liquid from which protons and neutrons formed, the hottest liquid that's ever existed, the most earliest complex form of matter. It's the most liquid that's ever existed. And as I said once earlier, all great discoveries open new doors. What are the new doors that have been opened here? What are the what next questions? I mentioned two, and I'll spend the last part of the colloquium on the second of these two. The first question is, what's its phase diagram? When you discover high-temperature superconductors, you say, oh, I've discovered high-temperature superconductivity. One of the next things you do is you ask, what is the phase diagram of this material as a function of temperature and doping? We ask the same question, what is the phase diagram of hot quark soup as a function of temperature and doping? For us, doping is excess of quarks over antiquarks. And This is a very interesting frontier in the subject. All of us are waiting with great anticipation for results from an experimental program at RIC that took 3 years of data to explore and is exploring this region of the phase diagram, seeking to answer the question of whether there is, notice the question mark, is there a critical point in this region of the phase diagram where a first order phase transition line begins? We may learn the answer to this question as soon as next month. The data taking ended in 2021. There's a conference next month at which it will be very tempting, I think, for the experimentalists to show first results. We shall see. Because they haven't shown first results yet, I'm going to focus on the other question. So the other question, which discovering this liquid opens up, is, well, how do quarks and gluons conspire to make a liquid? Why was it so hard? The theorists had 37 years with the laws of nature. Why wasn't it easy to predict that there's a liquid? So how does a liquid emerge from the fundamental laws that govern quarks and gluons? To do this, we need to probe the liquid. We need to see the inner workings of hot quark soup. And the first step to seeing what the quarks and gluons are doing in there is seeing the quarks and gluons in there, which is to say, we need a camera that can take a high-resolution, fast shutter speed look at one quark or one gluon at one moment in quark soup. Which is to say, we need to do for quark soup what Rutherford did for atoms and Friedman, Kendall, and Taylor did for protons. So we need to take a drop of hot quark soup from Geneva to Stanford and shoot that beam of electrons at it. Sadly, that's impossible because the drop of quark soup only lives 10 to the minus 22 seconds, and that's not enough time to get it from Geneva to Stanford. So somehow we need to probe this stuff, but we have to use a probe that's made in the same collision that makes the soup. And that's where jets come in again. Because in the same collision that makes the soup, once in a while, not an electron, but a quark from one nucleus can hit a quark from the other nucleus at such high energy as to make a jet, and that jet will become our probe. And I didn't pause on this, but look at this event right here. This is the debris from the explosion of the soup. What's this sticking out right here? Or look at this event right here. Here's the debris from the collision of the soup, but what's this sticking out and what's that sticking out? These are jets. So these are events in which in the same collision you made a little bang, a blob of soup, and a device with which we can probe that soup. You have very little control over the device. You didn't construct an accelerator. You take what nature gives you. But here we have a spray of very high energy quarks and gluons flying through the soup that ultimately turn into ordinary particles which are detected in the detector as these jets. So at the cartoon level, here's my blob of blue quark soup. Right there was a very hard scattering that made a spray of particles going this way and a spray of particles going that way. If this were in vacuum, no quark soup, I get two jets back to back. In the blob of quark soup, these jets have to shoot through the soup. They're going to get modified. And they're going to get modified in two sorts of ways. One thing that could happen is Rutherford-like. Maybe I'll be so lucky that this quark here scatters at large angles and comes off like this. That's Rutherford for the third time in the colloquium. But there's other physics that happens. When you shoot a bullet through water, it makes waves. So the other thing that happens when you shoot these jets through this blob of quark-gluon plasma is it will make waves in the liquid. That's actually interesting in its own right. How do you study material? One of the ways you study materials is you look at the waves in the material and see how they propagate and damp. So all of a sudden we have these jets in the soup. We can look for Rutherford scattering, we can look for waves, but that's what the real data looks like. So this slide, actually on this slide is written what I just said. Jets are the best chance we have of doing a Rutherford scattering experiment, and they're also the best chance that we have of seeing ripples in the soup. And the fact that there's two very different sounding kinds of physics that are encoded in the same events tells us that this is going to be very hard because we have to decode from the data both of those kinds of physics and more. Just to give you a sense that jets do get modified by the soup, this was day one LHC. Day one LHC, you saw a 205 GeV jet back-to-back with a 70 GeV jet, same at Atlas. This is not the violation of energy conservation. This is one jet here got much more degraded by the soup than the other jet here. So jets do get affected by the soup. We've known that for quite a while. But we need to learn, we need to train our eyes to use data on jets to answer questions about Rutherford scattering off of quark-gluon plasma and ripples in quark-gluon plasma. So how do we train our eyes? Well, this to me is the use of a model. Guy mentioned 12 years ago we started on something that was just what if. That something was the development of a model. What are models good for? To me, the most important reason that it's worth using models as a theoretical physicist is that you can do things with them that you can't do with data. An experimentalist cannot turn off momentum conservation. So if I go back to this cartoon, I could ask the experimentalist, could you just turn off the wake, please? We'd like to study the Rutherford part without the wake, so just turn off the wake. Experimentalists can't do that because momentum conservation requires that if the jet loses momentum, it makes waves. We could ask the experimentalist, could you turn off Rutherford scattering? We'd like to just look at the waves. Experimentalists can't do that either. So, but in a model, we can. I'm not going to go through the slide except to say that the model that I'm going to describe was developed by a set of authors that includes Guillermo Emiliano. There he is. He's on all the papers in which this model was developed. I hope he will forgive me for saying that the person I really want to highlight is Danny Pablos, who is also on all of the papers. In many ways, Danny has been the soul of this collaboration. He has really led this work from beginning to end. I hope Guy will agree with me in saying that. So here's the model as a cartoon. There was more on the previous slide, but I want to just use the cartoon. So here's my blob of blue soup. Here's a jet going through it. And what we do in the model is we suppose that every quark or gluon in this jet is losing energy to the soup. And we say that the amount of energy it loses, dEdx, energy lost per distance travel, is described by this formula. Where did this formula come from? This formula came from a string theory calculation that was valid for a very strongly coupled soup in a cousin theory of QCD, because we don't know from first principles in QCD itself actually how to calculate this dEdx. So we took this from a place where it had been calculated in an analog theory. There is one free parameter in this formula. It's sitting right there. We fit this parameter to experimental data. We don't take it from the string theory calculation. Then these bullets are losing energy to the soup, so the soup has to have ripples. We described that also. We've been describing that since 2016 in a very crude way. And what have we done with this model? We and many other theorists have taken many key steps in the past 5 years or so, 5 to 10 years. Examples of the kinds of things we've done are on this slide, which I'm going to show multiple times. These first two bullets I don't have time to walk you through, but I will say it's extremely important to learn how to disentangle experimental evidence for the actual modification of jets versus changes to how you select the jets. If you select 100 GeV jets in lead-lead collisions and compare them to 100 GeV jets in proton-proton collisions, you are actually comparing apples to oranges. The way you're doing the selection has different implications when the jets are going through soup. And so actually, you're changing the way you select jets can change your observable consequences. And this has to be separated out from actually seeing true modification of jets. This is a very important point, but I will say it's for the experts. Another important point, which I'll also say is for the experts, is you have to convince yourself that the soup actually doesn't respond just to the entire jet as one object, but it can see the quarks and gluons inside the soup. Because if you want the quarks and gluons in the soup to see the inner workings of the quark-gluon plasma, that means that the quark-gluon plasma has to be able to resolve the structure of the jet. And that also, these slides that I will skip are us convincing ourselves of these two facts. So the next two bullets are where I will spend the last part of my time. This will be how we use the model to train our eyes to look at the wake, the ripples that a jet leaves. And this will be how we train our eyes to look for Rutherford scattering. So this first. This is the theorist's confession slide. Our treatment of the wake is very crude. Guy and I and our collaborators are busy working on a much better treatment of the wake. This is in progress. We will be able, everything that we say about predictions for what the wake will look like will get much better when we finish the work we're in the middle of. So I want now to show two new observables that teach us how to use data to look at the wake. The first one is in work done with Danny, who I've already mentioned, and Arjun, who's a master's student at Cambridge University. And what Danny and Arjun and I are asking is, do subjets have separate wakes? Let's look at a jet with two subjets. How are we going to look at a jet with two subjets? Well, we do this in a way that Atlas introduced. So we take an observable that Atlas introduced in 2019. This is the paper in which they report their measurements of this observable. And our perspective is that what Atlas has done, the recipe is in the bullets, but ignore the recipe. They have a way of finding jets with two spikes inside the jets. So they can find jets in which there is a subjet like this and a subjet like that. And they can find events in which those two spikes are 0.6 to 0.8 radians apart or 1.8 to 2 radians apart. So basically, they have a way of finding jets in which there are two spikes that could be any angle apart. Atlas introduced a way of selecting events with these characteristics, and now we do something that Atlas cannot do. We look at the wake of jets with, first of all, one spike, and then look at all of these panels. This is jets with two spikes that are 0.7 radians apart. They're very far apart, but they have a common wake. Make them farther apart, farther apart, farther apart, farther apart. By here, you can see two wakes. They're pi by 2 apart here. So you have to make them almost pi by 2 apart before the wakes start to separate. So we found a way, as theorists, to visualize the wake of jets with two subjets. What can experimentalists do? Well, we then look at experimental observables and ask which ones are good proxies for what I just did. This is pretty good. If you look only at the particles in the jet with PT less than 1.5 GeV, this one is actually even better. If you can look at the soft particles in a jet and look at those jets that have the two spikes, and then look at the soft particles in the jet, that, we say, is a very good way of looking at the wake and seeing how one wake separates into two as you separate the spikes. This is something that both Atlas and CMS have told us that they can do. We look forward to seeing the data. Here's the second example. So is Carlotta here? There she is. Carlotta and probably others in the room are the world experts on energy correlator observables. So I'm taking a risk here and showing unpublished work on energy correlators with Carlotta in the audience. You can ask her about all the things I say that are wrong. But we have found an energy correlator observable where if you look at that observable, including the wake, it looks like this. And if you look at that observable ignoring the wake, it looks like this. And what you see is that this is an energy correlator, which experimentalists have not yet measured, but CMS and Elise are both planning to measure. And we have said that we're training their eyes. We're saying that you should, if you see something like this, this is coming from the wake. if you see something like this, well, we say you won't see something like this because we say that jets will have wakes. This gives you an idea of how and both these calculations are coming from the model that Guy and Danny and colleagues introduced 12 years ago, which it's hard for me to believe that it's been 12 years. Last part of my colloquium, how do we look for Rutherford scattering? This is work done by Danny, Zach Holcher, and me. Zach is a student at Stanford. What we're going to do is we're going to add hard scattering to this hybrid model. I've already motivated why this is a good thing to do. We want to look for this hard scattering. It's not in the model that I've described so far. Nothing in the model involves scattering at 45-degree angles. We had better add that. And once we add it, we can turn it off and on and see its effects. And so the way we add it is we build upon a calculation done way back in 2019 of here is a quark shooting into a brick of Big Bang matter. We calculated the probability of scattering with angle theta. And we had plots like this. We had plots like this. Now we add that to the model. We go back to this model. This is the cartoon from before. And we say, did this particle scatter? No. Did it scatter? No. Did it scatter? No. Oh, right there was a scattering. Oh, right there was a scattering. And those scatterings change this jet into this jet. This is obviously a cartoon. But this cartoon tells you what we should look for to see Rutherford scattering. We should look for changes in the subjet structure of jets. So I'm going to show you a bunch of plots from the model in which we do something in the model that experimentalists cannot do. We turn the Rutherford scattering off and on. We turn the wake off and on. When they're both on, it's the red curve. When they're both off, it's the black curve. Green is Rutherford scattering is on, wake is off. Blue is Rutherford scattering is off, wake is on. Experimentalists cannot do this. We can. And these are two classic, venerable, old friend jet observables called jet shape and jet fragmentation function. Anytime you see an observable in a plot like this where red is with blue and green is with black, that means it's sensitive to the wake, but the effects of Rutherford scattering are smaller than the effects of the wake because Rutherford scattering separates blue from red and black from green, whereas the wake separates blue and green from red and black. So these venerable, familiar, long-studied jet observables are not good ways of looking for Rutherford scattering. They do show effects of the wake, however. So then the next idea, which in fact I think I'm one of those responsible for suggesting, turned out not to be a good one, as Elise showed. The next idea is, well, suppose I have two back-to-back jets. Can you look for a deflection of one of the jets? And in light of the time, I will just say that Elise has measured this. They've seen the effect, but the systematics of what they see don't look like Rutherford scattering. And in fact, we can describe the systematics of what they see in our model. And red is with blue, green is with black. It turns out to be an effect of the wake. So what I missed when I made this suggestion 10 years ago to look for deflections of the entire jet is that the wake of a jet makes it much harder to see what was the actual direction of the jet, and that fakes a deflection. So it turns out that the fact that jets have wakes, the fact that when jets go through the soup, they create a wake, that obscures any possible deflection of the entire jet. So what should we do? We should look for ways of looking at jets that are insensitive to the wake. And these are examples of what are called groomed observables, where you groom away the soft stuff. And look, red is with green, blue is with black. Here's another one. Red is with green, blue is with black. That means Rutherford scattering separates red from blue. The wake separates red from green. That means these observables are more sensitive to Rutherford scattering than to the wake. And the one I want to focus on is this one in the top left corner. This is, it's a groomed observable that tells you, you look inside a jet and you ask, what's the angular separation between the two most prominent structures in the jet? And here's 0.1 radians, here's 0.15 radians. And then this tells you, is it more or less likely to see a jet whose angular structures inside of it are 0.15 radians from apart in lead-lead versus PP? 1 means lead-lead is just as likely as PP. So red and green together, blue and black together. This big difference here is from Rutherford scattering. That's good. But this red and green here are still below 1. I just told you that Rutherford scattering, there's a new physical effect when jets go through soup, which is that particles in them can scatter at large angles. If it's a new physical effect that's not there in PP collisions, shouldn't this red and green be above 1? It's a new source of scattering that it makes it more likely to get these structures at these angles. This should be up here. What's it doing down there? The answer is selection bias, something that sounded boring and technical to you when I mentioned it briefly before. It turns out that we are biasing in the direction of selecting jets with less structure. And it turns out I can control the bias. I'm going to change the bias. Aha, I can change the bias. How did I change the bias? I changed the bias by what the experimentalists were doing here was, right there it says xj bigger than 0.4. That means they were looking at jets back-to-back with a photon. And they were saying if the photon has 100 GeV in energy, we'll look for jets bigger than 40, 0.4 of 100. We said, well, you know what? You're missing some of the most degraded jets. You have to look at jets with xj all the way down to 0.1. That's 10 GeV jets. Then you'll see Rutherford scattering sticking up like this, hitting you in the face. We said that, and we talked about how to control the bias. And then CMS went and made the measurement. These are slides from a talk by Letizia Cunquero, shown at a conference in Trento that Carlotta, and was Fabio an organizer also? No, Carlotta and colleagues organized. And this gray is the data. Gray is the data. They're changing the selection bias. These are most biased. These are less biased, but they're not unbiased. And this change as you change the bias going from, let me get the two that matter, going from this, which is most biased, to this, which is less biased, but not unbiased, you'll notice that that change looks sort of like what you see in the data going from the gray data here to the gray data there. But the effect of unbiasing is actually bigger in data than in the model. So if you look carefully, you will see here that this data agrees with Rutherford scattering. Rutherford scattering is the blue here. So if I was so foolish as to ignore the left half and look only at the right, I would say that Letizia Cunquero and the CMS collaboration have discovered Rutherford scattering. I will not say that because our model fails to describe this data. And the reason is that there's more selection bias effect in the data than in the model, which is something we have to understand. And we've now, Letizia and colleagues have said that the way they're going to go after this is by looking at higher energy photons, which will allow them to go to smaller values of xj. It will take them 2 years to do that. We did it in the model in a week. And this tells us that this is what they should be looking for. They'll have data this time next year. This time next year. OK, and we showed them how they can vary the selection bias in the data that they will be taking this coming November. And I will go then to the end. This is another observable with which to look for Rutherford scattering, which I don't have time for. So 2 concluding slides. What I've showed you in the last 15 minutes is how we can use a model to train our eyes to look for Rutherford scattering and ripples in the soup. We learned that some of the most venerable jet shape observables that have been studied for decades are not good ways of looking for Rutherford scattering, which people actually call Molière scattering for no good reason. Grooming helps. You groom away the soft particles. You then find the effects of Molière scattering dominate. We then showed how to engineer observables to either reduce or enhance the selection bias that can, when the selection bias is reduced, we showed that hard scattering, large angle scattering, Rutherford scattering will produce, will kick you in the face in the way that I showed a few slides ago. The kinds of observables that we're talking about are observables that cannot come from the wake, because the wake is a big schmear, and we're talking about angular structures within the jet and changing the angle between them, and the wake does not do that. But we've also seen new ways of looking at the wake. So I now come to this slide that I've shown 4 times previously, and I'll now end with the last 2 bullets on it. I've tried to set you up to invite a speaker, maybe Carlotta, maybe Liliana, where's Liliana, to speak about this subject again in a couple of years, because I really think we're just on the edge of a golden age of jet physics and heavy ion collisions. We're just on the edge of seeing the ripples in the soup that the jets make. We're just on the edge of doing the Rutherford scattering experiment off of quark-gluon plasma using jets. What we've been doing with theory advances, I've shown the ones I've shown. There are many others from many other people. And the analyses of today's early data is training our eyes. It's teaching us how to look for the microscopic effects of hard scattering and see the microscopic structure of the soup. It's training our eyes and teaching us how to look for the rippling of the quark-gluon plasma. All of this is whetting our appetite for the feast that will be coming soon, because at RIC, there's a new detector called S-Phoenix, which begins taking data next week, I think. At the LHC, we're in the middle of run 3. We have run 3 and run 4 over the next about 5 years, 6 years. And so I think the experimental data that will come from RIC and the LHC, we now have trained our eyes to look at it such that we will be able to use it to answer the question that Rutherford first answered for atoms, that Friedman, Kendall, and Taylor first answered for protons, but we will be answering that question and more for little droplets of the Big Bang that are being created in these collisions. And I will stop with that.
Thank you.